Hi, and welcome to the Mathspace Academy for Year 12. My name is Andrew. I'm the head of content here at Mathspace, which means that if you're doing a question in Mathspace, if you're looking at a lesson, if you're looking at an image, if you're doing anything mathematical, it's almost certain that someone from my team has worked on it and made it as good as we can make it. We're constantly improving, and we read every piece of feedback that you send us. So please keep sending that feedback. We really enjoy reading all the things that you have to say about us. So the other thing is that this is a course that is addressing the New South Wales curriculum, which means I'm going to be looking at a New South Wales textbook. If you aren't from New South Wales, don't worry. Everything that I show you, you'll be able to find in your own version of the textbook. You might be surprised to learn that different states have slightly different things in their high school, but nothing I talk about today is going to be like New South Wales only or something like that. So it just might mean that your textbooks and the textbooks you have available might be a little bit different. Everything's going to make a lot more sense if you are in Mathspace yourself, if you're logged in. If you don't have a Mathspace account, then ask your teacher if you have Mathspace through your school. And if you don't have Mathspace through your school, then ask your parents to take a look at the Mathspace main website and look at our homeschooling tutoring service. The other thing is that if you want to learn a little bit about networks, that was what I covered last week. I didn't do the critical path analysis because generally speaking, I think that your teachers probably left that till later in the year. But in terms of things like flow networks and minimum spanning trees, you can view the recording over at the Mathspace Academy website. So I'll just pull this one up. This is what it looks like. Here we go. So there's my face there. And then if you go to year 12 and click into year 12 here, this is what we're doing today. We're doing trigonometry. And you can see down here, networks, if you want to view that recording. So everything's recorded, and you can see sort of what's coming up. Seems to be in reverse order, but I'm sure you'll figure it out. The next thing is I do have the chat and the Q&A sections open on my other monitor. Now I'm just going to let the chat scroll by, and so feel free to use that to talk amongst yourselves. If you actually want to get my attention and ask a question that you want me to answer, then use the Q&A feature. The Q&A feature looks like two little speech bubbles and it's at the bottom there. So that's enough introduction. I'm going to jump in and show you what the student page is looking like and what you might see when you're logged into Mathspace. So as I said last week, David Bowie dinosaur avatar, best avatar. You can choose another one if you like, but that one's the best one. So this is me logged in on my student account. And here I've got all the tasks that my teacher might have sent me. I've got lessons, I've got some exploration. But when you're doing your own work, the best place to do it, in my opinion, is over here on the topics page. If you click into topics, you'll see the textbook that you have selected and how far you are towards mastering various parts of it. So right now I can tell that I'm looking at New South Wales Math Standard 11. I don't want Standard 11, I want Standard 12. We're in year 12 now, okay. So then we go Australia, New South Wales, and then New South Wales Math Standard to year 12. So I'll do that one more time. Just click up the top here, and you won't have nearly as many textbooks as I do. We have a lot of textbooks here at Mathspace. But you click on Australia, then click on your state. If New South Wales isn't available for you, maybe you're in Victoria or somewhere else, then you just click on the state and then you click on the year level that you want. So Math Standard 2 year 12, click on that one and we're loaded in. So networks was the topic that we covered last week. Today, I'm going to be doing a bit of revision on trigonometry. If you click into trigonometry, you might find some of these bars are already filled up. And if you can fill up all of these bars all the way to the end, then you will have mastered everything you need to know about trigonometry before your final exams. So it's a really good idea, especially when you're working on your own. Maybe you've done all the work that your teacher set you, or you just want to explore things on your own, then the best place to do it is the topics page, and try and push all of these bars to the top. That'll push all of these bars to the top. And then if all of these are filled, then you're going to do really good on your exam at the end. So that's trigonometry is what we're going to be looking at. But I'm going to be concentrating most of my efforts today in the textbook, even though I'm going to spend a little bit of time in GeoGebra as well. Okay, so I'll get rid of my student account and I'll get rid of this. I don't need this anymore. And you can see my incredibly messy desktop while I find the other thing that I was looking for. Yeah, this is the one. Here we go. Trigonometry. So first up, before we go anywhere and do anything potentially more interesting, I want to talk about Pythagoras' theorem. Pythagoras' theorem, it's a word that you've probably been hearing for years now. And why do we use Pythagoras' theorem? I'm going to assume that you know it and you've seen it before, but what is its purpose? When do we use it? It's whenever we know two sides of a right-angled triangle, we can find the third one. Okay, but why do we even care about right-angled triangles anyway? Well, the secret is, why do we care so much about right-angled triangles, is that any shape can be broken up into right-angled triangles. So you might as well ask a chemist why they care so much about atoms, about elements, or a physicist why they care a lot about protons and electrons. They make up everything. So I'll just by way of demonstrating, you can draw any old shape. So here is this definitely a shape. There we go. And you can break it up into right-angled triangles. So I'm just going to start by breaking it up into triangles like this. There we go. And then I can break them up into right-angled triangles like this. There's a right angle there. And like this. A right angle there. And then like this. A right angle there. So I've taken a five-sided shape and I've turned it into 6 right-angled triangles. So if I can understand everything about right-angled triangles, everything about them, then I understand every shape. No matter what kind of crazy shape you might want to draw, right-angled triangles are the basic building blocks of everything in geometry. So if you've ever wondered, why are we Pythagoras? How do you even spell that? What's the point of all this? It's because right-angled triangles are super important, and the Pythagoras' theorem will let you, if you know 1, 2 sides, you can find the third one. And it doesn't just have to be the 2 short sides. You find the 2, if you know instead one of the short sides in the hypotenuse, you can find the missing side. This is handy for all sorts of applications, especially in trades, but also in engineering and even in computer applications. I had a friend of mine contact me the other week about 3D modeling questions, and because he's making a video game, and it ends up just coming down to a whole bunch of Pythagoras and a little bit of trigonometry. So it really does come up absolutely everywhere. And so that's why you've been hearing about Pythagoras for a while. If I'm the first person to tell you that, that's good to hear. One of the things that we always want to do in maths is make sure that we're asking the questions about why we're learning something. Okay, so I'm going to assume that you know Pythagoras' theorem, you know how it works, and you know how to use it. If you don't, I think the best thing to do is to go into Mathspace, find that Pythagoras theorem topic, and see if you can master it. Read this lesson and go on from there. But instead, what I'm going to do today is I'm going to talk about trigonometry. Trigonometry is when we start getting things like sine and cos and tan involved. So to do that, I've actually prepared a little bit of a GeoGebra. You'll see GeoGebras cropping up all over Mathspace, and they exhibit some property, and we make them on the content team to try and illustrate some concept or principle or something like that. So what I've got up in front of me here is a triangle, a right-angled triangle. And we'll think about the kinds of questions we're going to have to answer in a second. I just want to focus us in on this right-angled triangle. Because remember, I said, if we understand right-angled triangles, we understand every shape ever. You can even start doing this stuff and doing it into 3D, and it's like atoms for geometry. So what this little slider does is it changes that angle in the bottom left. But notice that this side here, the hypotenuse in Pythagoras' theorem, is fixed. I've fixed it at a length of 1. So I can change this and the triangle will move around. That's because if you add up all the angles on the inside of a triangle, it makes 180 degrees. And this right angle is super greedy and eats 90 of them. So if this angle here is 33.6, then this angle here plus this angle here is going to be 90 degrees. This means that as this angle gets bigger, this angle gets smaller. And goes up. Here we go. So that's a little bit bigger. That one's a little bit smaller. And then back this way. That one's smaller. That one's bigger. Okay. But with this, I can build all sorts of different right-angled triangles. Only ones that have a hypotenuse of 1. We'll get to the next bit in a second. But because I've fixed the hypotenuse length at 1, what I'm doing when I am changing this angle, think about the shape that B is tracing out. So this B is moving around. What happens if I keep B moving around and I get B to move all the way over around here? It's still moving around. It's starting to make a little less sense what this angle means, but just stay with me. And if you've been super observant, you might have already guessed that this says show circle for a reason. This is me moving this triangle around on a circle by moving this point B. Okay. What changes as I move this slider around? I know that this length doesn't change, but I'm going to start things off all the way down here at the bottom, and I'm going to take a look at the vertical height. So think about what happens to the vertical height as I increase this angle. Increase, decrease, increase, decrease. Okay, so I'm going to go all the way down to 0. It's not a very interesting triangle, but I'm going to, this time, I'm going to track what happens to that vertical height as I move it. So here we go. Whoop, it starts off, and as I can see, as I increase the angle, that vertical height gets larger and larger. It starts slowing down a little bit until it gets up like that. So that's the vertical height. As the angle gets bigger, the vertical height gets bigger. All right, let me rewind this. And instead, let's take a look at the horizontal distance. Horizontal distance. Up. As we increase the angle, what happens? Well, this side of the triangle gets smaller and smaller, smaller and smaller, smaller and smaller, until it gets down to 0. So the vertical height starts off small and gets big, and the horizontal distance starts off big and gets small. What happens if I keep going around? Let's go all the way around the circle. It's not going to make a lot of sense because that angle is going to be outside of the triangle, but what do we get? And so let's start it off at 0, and let's track them both at the same time. What do we get? We get this. Now these curves you may have seen before. These are called sine and cosine, and they just keep repeating themselves in this wave motion. the vertical height one is this one. I'll just take it back so we can see it go around again. It starts off at 0. It gets to its maximum when the triangle's really tall and thin, and then we go back down again. And then it goes under, gets to its maximum and comes back. And then it just repeats itself. Okay. Now, what about the horizontal distance? Instead, it goes up from maximum when it's all the way at a very thin and short triangle, and it's at its minimum when it's thin and tall, and then down and up and down and up and down. We give special names to each of these sides. We call this side cos and this vertical one sine. And notice how the length of each of these is entirely determined by this angle here. You may not have seen this curve before, but it also gives you a bit of a clue about why we care so much about triangles. Remember that I said at the beginning that triangles are like the atoms of every shape ever? Well, think about what kinds of things go like this. What kinds of things go up and down like this? Imagine that this is like, instead of an angle, let's forget about angles for a second. What kind of phenomenon might go like this? Up and down, and up and down, repeating itself. Things like the amount of sunlight that is outside. It goes up, and then it goes to 0, and then it goes up. Something like the tides. They repeat themselves over and over again. So it's not just shapes that triangles help us understand. They can tell us all sorts of things about interesting phenomena in the world. And it all comes about by just being super obsessive about right-angled triangles. It's crazy, but that's the kind of thing that mathematics does over and over again. It's just, you go, right-angled triangles are connected with like the tides, and the answer is yes. So now that we've got both of these graphs and I've talked about the horizontal distance and the vertical height, I'm going to show you the picture, the one picture that you need to remember whenever you're doing anything in trigonometry. And it looks like this. So let me just take you through what I've got written here. So first of all, this theta, it's a Greek letter, and it's because we get sick of using X and Y and Z all the time, and also the Greeks did a lot of this stuff in the beginning. So it's kind of a nod to history. This is theta, the angle, and what I've been calling the vertical height is called sine of theta. Whatever this angle is tells me what the vertical height is. And the vertical height, which is sometimes called opposite the angle, because the angle's here opposite this blue one, this is the sine theta. And red is the horizontal distance, and that's cos theta. After this 15 minutes, I'm sure you'll go back to pressing the sine button and pressing the cos button on your calculator. But what it really means is when this is an angle, how tall is the triangle and how far across is the triangle? That's what these thetas mean. But also notice that I've changed this 1 to a k. Why k? Well, it can be any size I like. If I zoom in and out, the proportion of the sides stays exactly the same. So if this is a 1, this would be sine theta, and this would be cos theta. But if the hypotenuse was 2, then this would be 2 times sine theta, and this would be 2 times cos theta. 3 times sine theta, 3 times cos theta. This angle, we're going to be knowing at the beginning. We're going to start by knowing this angle, and we're going to be trying to find one of these two sides. There's also another one, which is called tan, which we'll get to in a second. But just remember and try and keep this picture in your head when we go into the rest of Mathspace and start finding some unknown sides. Okay, so minimize this. Let's go back one step. What was Pythagoras useful for? Well, if you had two sides, then you could find a third side. I know this side, I know this side, I can find this side. Everything I just discussed, the sine, the cos, the tan, we're going to use it when we know one side and one angle. If we know one side and one angle, we can find a missing side. So let's go into finding unknown sides and take a look at a question in there. Line this up. We'll talk about tan later. Okay, let's do this one. I will mention, I mentioned this last week, but I'll do it again. Here I am looking at the textbook section. I'm also in my teacher account here, but your textbook section will look very similar. Whenever you do try question, it's not going to give you any credit. That's why I reckon going through the topics page and clicking on practice is the best way to get your point, get credit for your work. Okay, let's have a crack at this question. So first of all, what's different about this triangle than the triangle that I was looking at before? So let's notice a few things. First of all, this isn't 1, it's 12. Okay. So we got to keep aware of that. This is a little bit different. Also, the angle's up here, not down here. So I'm going to redraw this, and I'm not going to use my, I'm going to use my pen for this one. Pen. So I want this angle to be down the bottom, like it was before in my GeoGebra. There's my right angle. So instead of the 34 being up there, I'm going to reflect this. So the 34 is in here, 34 degrees. Okay. Okay. Now this is still 12. 12. And where's this F? Well, one thing I can notice is that the 34 degrees is between the 12 and the F. So by moving the 34, by sort of reflecting it, I've put the F down the bottom here. F. Centimeters. Okay. So remember that picture that I had for you before? This conclusion picture. K, theta, and K cos theta. Well, let's map that. Well, let's map that across here. 12 is K. 34 is theta. And F is K cos theta. So I'll just, once again, I'll go back, match them up. K, the length of the hypotenuse, is 12. Theta, that's the angle in the bottom left, that's 34 degrees. And then there's F down the bottom here, that's K cos theta. So this length here, F, equals 12, this number here, times cos, and you can tell it's cos because it's this horizontal distance. It looks like a vertical height in the original, but that's just because the angle's up here in space. If we put the angle in its proper spot, we can see that F goes along the bottom here. Cos 34 degrees. Now, maybe you've never seen this approach before. Maybe you just go SOHCAHTOA, plug it in. I encourage you to give this a go just to see if maybe something will click. Maybe something that you've seen before a million times, maybe this time it'll come through. I'll show you the SOHCAHTOA approach in just a second, but I wanted to connect it with the GeoGebra that I was doing just before. So I type this in here. Good question. So someone's asked, why did I bring the 34 down? And that's because I wanted to match it with the way that this circle worked. So remember when I was doing this circle, the angle was always in the center there. And cos was my horizontal distance. And sine was my vertical height. If my angle is up here, then it doesn't match the picture that I was trying to draw before. If you're good at spatial rotation, you can move it around, but if by moving it through here, you can see why I'm using cos. If the angle is in the bottom left corner, then cos is always going to be the horizontal one, and sine is always going to be the vertical one. But if the angle isn't there, you might get confused and might get it round the wrong way. F here is vertical, and so you might think, oh, I'm going to use sine. But instead, this 34 is in the wrong spot. If I move it down here, I'm like, okay, it's actually the horizontal one. I hope that answers the question. Feel free to answer another one if I didn't quite nail it with my explanation there. So, when it says here, find the value of f correct to 2 decimal places, well, I can actually enter this into Mathspace just as an equation. Because there's no equal sign here, I'm going to have to put the equal sign in myself. F equals 12 cos 34, and then I hit enter. It's asked me to do 2 decimal places, so I'm going to get old mate Google to help me out here. 12 times, got to do an asterisk symbol for times, that's shift 8. 12 times cos 34. Hit enter. Oh, it's giving me radians. Okay, I'll write in degrees. You might say to yourself, what's radians? Don't worry. If it says radians, I'm sure you've had it on your calculator. Everyone has a different model of calculator and everyone has to change it out of radian to degree mode. But just make sure that it says degrees if you're ever using the Google calculator, or maybe your calculator does degrees, but the way I could tell that was wrong is because it was giving me a negative answer. So this is my answer, 9.948. I've got to give it to 2 decimal places, so I round up 9.95. F equals 9.95. Okay, but whatever, the calculator part isn't important. The important part was us matching this up with the picture that I gave before. We're going to try a different one using the same sort of picture. And as I said, you're probably way more familiar with SOHCAHTOA, and you can actually get SOHCAHTOA out of what I showed you. But I reckon you'll have a shot at doing something a little bit different. Okay, let's try this one. If you think about it my way, just as a suggestion. All right, I'm going to do one more of these, and then we're going to talk about finding an angle. Okay, now this time the angle is in a kind of a weird place. What's different about this and comparing it to the picture I showed you before? Well, this time the angle that we care about, the theta angle, is in the right spot. It's in down in the bottom left here. But this right angle is all the way up in space. And we always want our triangle to look like this, where we've got our triangle, we've got a right angle, and then the angle that we care about is down here in the corner, 43 degrees. Okay. So if that's 43 degrees, then which one is G and which one is 7? Well, let's think about it. This G is the hypotenuse. I can tell that because it's the long one and it's opposite the 90-degree angle. So I can put G over here and I can put 7. Where's 7? Is it this one or that one? Well, notice that the 7 is opposite the 43. It's not the one touching or adjacent to 43, it's opposite the 43. 43, 7 is across the other side. So 43, and that's 7 up here. Okay, 7. Oh, okay. It looks kind of like a 9. I'm just going to make it a little bit more curly, like a G. Okay. So remembering our picture from before, G is that hypotenuse length. But what's this 7? Well, 7 is the sine, because it's the height one. I'm just going to flick back here. In here, I've got my theta. That's this 43 degrees here. I've matched that up right. I've matched up my right angle correctly, looking good. I've got my hypotenuse, that's that K, but I've got this vertical bit that's K sine theta. So how do I express 7? What do I do with that? Well, I know that 7 is equal to the hypotenuse length, which in this case is G. And then because it's the vertical height, since I've oriented it correctly, it's sine 43. And in this particular problem, I need to find G. So last week I talked about networks. But if you're feeling a little bit funny about your equations and whether or not you multiply or divide, maybe check out my year 11 lesson from last week where I went through formulas and equations. But because I want to find G and it's getting multiplied by something, I just divide by the something. So I can write G equals 7 divided by sine 43. Good question. I just had a question come through. Why is it 7 equals G sine 43 and not G equals 7 sine 43? So I'm going to answer this one. Let's take a look at matching up with the picture that I gave you. This one here, K sine theta, matches up with my 7. So 7, do I still have my last one up? Yeah, okay. So let's take a look at the previous one to contrast it. So here, the number that I knew was on the hypotenuse. And the number down the bottom here is F. And then when I translated the equation across, it's the length of the hypotenuse times cos 34. So I got this equation. But notice the thing that's different here. The letter is the hypotenuse, and the number that I know is 7. So writing it out, 7 is the length of the hypotenuse times sine 43. That's just applying exactly the picture that I had over here. 7 is this thing. 7 is K sine theta. That's just matching it up. Whereas in this one, I read it off and I say F. What's F? Well, F is K cos theta. 12 cos 34. And this one over here, this one, 7, matching it up, is K sine theta. 7 is K sine theta. In this instance, the tricky part though is that the K, the length of the hypotenuse, is unknown. So once again, I hope I answered your question, but feel free to feel free to send through another one if you want me to have another stab at it. So all I'm doing is I'm matching this up with the picture, and I'm saying, well, in this picture here, it says 7, and in this picture here, it says K sine theta. So I just write 7 is equal to K sine theta. In this instance, we've got our G over here. We go back to old mate to get our 7 over, what was it? 7 over sine 43. Sine 43 degrees. Thanks, Google. 10.26. Bingo. Okay. One last one that what I want to do now is I want to talk about SOHCAHTOA. SOHCAHTOA is almost certainly what you've been doing this whole time. It makes sense. It's just a thing. You just turn the handle, whatever. I decided to show you this today just in case playing around with this idea will help it really lock it into your brain. So let's try it instead with SOHCAHTOA and see what's different. The way that SOHCAHTOA works is it's a mnemonic, and it says sine theta, that's the S part of SOHCAHTOA, equals the opposite side, opposite side, it looks like a 6 over hypotenuse. One day, someone will figure out how to make writing on the screen look really good. It is not today. And it is not me. Wow, that is rubbish. There you go. Sine theta equals opposite over hypotenuse. And what you do is you just plug the numbers in. Let's plug the numbers in. Okay, sine. Oh. Oh. Sine. Theta. What's theta? It's 34. 34. What's the length of the opposite side? It's 18. 18. And what's the length of the hypotenuse? It's G. And if you rearrange this equation, you get a very similar equation to the one that we had before. I like SOHCAHTOA because it helps you remember the important concepts. I don't like SOHCAHTOA because you can get just far enough to do some things, but then if you don't understand that picture that I gave you before, you won't be able to get all the way through to the rest of trigonometry, which is what I'm going to be talking about next week. So that's the sine part. The cos part, let's do this one again. How does it work for cos theta? Well, here we go cos theta. Cos theta. Oh man, I don't know why my pen's not working today. Cos theta, cos 34. Okay, my pen's messing up. We're just gonna have to mouse this. Cos 34 equals the SOHCAHTOA goes S-O-H-K-A-H. Funny story. Part of the reason why I don't like SOHCAHTOA is because the person who taught it to me was my year 10 drama teacher. My maths teacher never taught it to us. And I think it was really good for me. And then my year 10 drama teacher was like, oh, you know, trigonometry, like SOHCAHTOA. And I was like, what? SOHCAHTOA? Yeah. Crazy story. So 34 degrees is F over 12. A stands for adjacent. It's the adjacent side. And H stands for the hypotenuse, which is 12. And you can rearrange that and get the same equation that we got before. So if you're thinking to yourself, why didn't we just use SOHCAHTOA? That's cool. You probably already know what SOHCAHTOA is, and you can use SOHCAHTOA to get, you know, at least halfway through this topic. But if you think about that picture, you can actually think about how SOHCAHTOA comes about and make sure that you actually understand what you're doing. Because sometimes you go to yourself, SOHCAHTOA, which one? I don't know, I'll pick the sine one, I guess, and I'll just make this one H and O. And if you don't know how to use the tool you're using, you may end up not doing so well. So the final one I wanted to talk about today is tan. I haven't mentioned tan yet, but let's try and see, let's do the approach that we've been doing this whole time, except this time we're going to be doing it with this triangle. Try question. Okay. So I picked a question this time that we don't have to do any tricky rotation. It's a little bit tilted to the side, but if you turn your head a little bit, you can see how the triangle's in the same orientation as it was in the applet I was showing you before. So what can I write about this triangle, matching it up with what I did before? Well, I can see that my theta is 38 degrees and my side length here, which is cos, because cos is the horizontal bit, is 10. So I know that 10 equals whatever the hypotenuse is. I'm just going to draw that as a question mark. It's question mark times cos 38. Okay. I'm going to do the same thing for this side here. I'm just going to copy across from the same equation I was looking at before. I still don't know what it is, but I can say that F, which is this side here, F equals question mark times sine 38. And now, you ready for some mathemagic? We're actually just going to do a division. Whoop. Have you ever seen anyone divide equations by equations before? You saw it here first. Because I don't know what this question mark is, I get rid of both of them, just like cancelling fractions. And what am I left with? I'm left with F over 10 equals sine 38 over cos 38. Okay. And this thing here, this is tan. If you push the tan button on your calculator, this is what's going to be found. Tan is just the ratio. Do you remember in your, whenever you did linear equations, you do rise over run? Well, that's what tan is. Tan's just rise over run of the same triangle we've been obsessing about from the very beginning. The rise is k sine theta, the run is k cos theta. When you divide them by each other, k sine theta divided by k cos theta, it's just rise over run, and you get the gradient of this line here. So that's tan 38. And that also explains what the TOA in SOHCAHTOA does. TOA stands for tan is the opposite over the adjacent. And when I look at this picture here, tan 38, that's the T, is equal to the opposite side, F, divided by the adjacent side, which is 10. So once again, we're going to finish this webinar. You can forget everything that I talked about, and you can just go back to your SOHCAHTOA and you push your buttons on your calculator and you'll get all the right answers. But just in case you've never seen anything like this before, I wanted to give you a little bit of a picture about what's really going on down the bottom and how all of this comes about. So I don't think that you should actually be doing this manipulation every time you solve a question like this, but remember that tan really is, in a fundamental sense, the gradient of this line, just rise over run. The more times you can connect different areas of maths together, the easier it all gets. Okay, so let's actually stop talking about doing the question and let's actually do the question. Okay, I turn off the sketch pad here. I can write this up, F over 10 equals tan 38. Enter. Okay, cool. In order to get just F on its own, I need to multiply both sides by 10. I just move this one across. 10 tan 38. Let's go over to old mate and see what he has to say. What was it I had to do? 10 tan 38. 10 times with an asterisk, tan 38 degrees. 7.81. 7.81. Okay. So what I've explored today so far is how to go from a side and an angle and find the other side. You've probably done it a whole bunch of times, but hopefully you see some of what's going on down below. I notice I've only got 10 minutes remaining, so I think what I'll do, if anyone has any questions or anything you'd like me to show you, let me know now. But I think what I'll do instead, if no one, in the absence of any questions from the audience, I might go and see if I can find a question from this set later on and see how tricky it can get. Just because I want to make sure that when you hang up this call, you can jump straight in to 3.02 and get all the way through. So let's see what else the person who put this set has in for us. I think a lot of these things are similar. Yep, we can do that now. We can do that now. Lots of finding the lengths. Gets a little bit trickier when we start throwing decimals in. Just throw it in your calculator just like any other one. Okay, now we're starting to get a little bit confusing. Very similar to the other ones. Skateboards are cool, right? Ladders. Okay, let's do this one. So what's tricky about this one is that you don't get a triangle. There's nothing drawn for you. So all we got to do here is draw the triangle and then figure out what kind of thing we're going to use. So what I'm going to do is, I know it's about triangles, along the side of a rectangular garden, a diagonal path. Okay, let's get it started. Rectangular garden. Here's my rectangular garden. Let's do it. Okay, looking good. And it says here that the longer side of a rectangular garden measures 13 meters. 1, 3, killing it. A diagonal path makes an angle of 27 degrees with the longer side of the garden. Now you might think that sounds ridiculous, but you should talk to someone who does landscaping and just, they have to do more than just degrees. They have to go down to minutes and seconds just to make sure that everything lines up perfectly. So we got our diagonal path. This is how you get through the garden, one side to the other. And then it says that it makes an angle of 27 degrees with the longer side of the garden. So I think that means that it's this angle here. One of the things that's nice about rectangles is that this angle here, this 27 degrees, is going to be the same here and here. Both of these are going to be 27 because both of these are 13s. This one here. And these are both 27. 27 degrees. Oh man, I can't do my angles today. 27 degrees. 27 degrees. And I'm going to throw in my right angles as well. If the length of the shorter side of the garden is y, calculate y. So this is y, the shorter side of the garden. So what I'm going to do first is, what part of this diagram don't I need? Well, I can either pick the top triangle or the bottom triangle to care about. And because I've already written the y here, I'm just not going to care about this top part. But remember what I said all the way back at the beginning. Everything is just right-angled triangles. Rectangles are just two right-angled triangles stuck together. So because it might be confusing, I'm just going to get rid of all of this part. And then go, just ignoring the other parts of the garden. I'm just focusing on the bottom rectangle here. Now, remember what I did all the way back at the beginning. I was like, oh, you know, you've got to swap them around. It's at this point that I reckon I'm just going to go with SOHCAHTOA. Once again, I know I need to use trigonometry because I have a side length and an angle, and I need another side. So I'm going to go, what sides do I have? Out of O, A, and H, the opposite, the adjacent, and the hypotenuse, what ones do I have? Well, I've been given the one that is adjacent to the angle, 13. So I know this one. And I want to find y, which is the opposite one. I don't know what it is. And what links together O and A? You can think of it again as being like a rise over run triangle. O and A are linked together by tan. So I write it out. Tan of my angle that I know, 27, equals the opposite y over the adjacent, sorry, TOA. Tan is opposite over adjacent, over 13. And I can put this into my calculator. I just multiply both sides by 13, or I can just check in with Mathspace first to make sure that I'm getting it right. Y over 13 equals tan 27. Okay, cool. And then just like I did in the last problem, as soon as I've gone, so I won't keep going. I won't use Google and get the decimal, but just wanted to emphasize the tricky parts of this question. So first of all, I had to draw it. I didn't get a triangle. So drawing that triangle and representing all of that information is actually really hard. That's why it's all the way down the bottom. It is hard. And then I needed to figure out which I needed to use. These were the sides that I cared about, this one and this one, and it was the one that was adjacent and opposite this angle here. So I knew I needed to use TOA, the SOHCAHTOA, TOA part of SOHCAHTOA, and then I end up, once I've got this equation, I'm home. I have already learned how to do this in all the previous sets. The tricky part is drawing the triangle and deciding what equation to use. Okay, so as I mentioned, next week, I'm going to be talking about finding angles. This was all about finding sides. There'll be an email sent around asking for feedback. Last week, someone said I lacked energy. Thank you. I tried to spice it up this week. But yeah, send some feedback if you get that email coming through. And if there's something that you want me to cover, let me know. But next week, what I have slated for is doing some more trigonometry, taking a look at finding angles and some of the more advanced applications of trigonometry. I just wanted to make sure that everybody was super across the basics, the fundamentals of right-angled triangles, why we care about them, and that sort of very basic picture, this one up here. This is in your head, you will go very far in trigonometry. Okay, thanks very much everyone for joining me, and I'll see you all next week.